not doing anything new today, really. We're doing adding and subtracting and multiplying and stuff like that. But we're doing it with polynomials, which you may not have done a whole lot. So, but it really is just basic math today in many, many ways. Let's go to the grade screen and see where we should be. You should have everything done through 2.07. And look, this week we're going to finish up the unit. We have this one lesson and the test. One lesson and the test. And there is a practice test for you to use that you can take the practice test and see if you're ready for the test. But the one lesson is what we're going to cover today at 2.08 polynomial operations. And then, you got the test this week. So let's go take a look at this one lesson that we're covering. Polynomial operations lesson. And it's going to start right off with the video. First thing. Oh yeah, these little funny looking little cartoons they got about this little girl who looks like she's 40. Sorry, just to me she looks like a 40-year-old woman. All right, let's see what it's got here.
Is everything okay in there?
I'm fine, Dad, but the picture I took during our Grand Canyon trip fell and the frame broke. The picture looks fine, but the frame is trashed.
That's all right. It can be replaced.
Okay, I'll go get a measuring tape.
I've got a better idea. Let's use your algebra skills to find the measurements. If you get the answer right, I'll buy you a new frame.
All right, I'll give it a shot.
Let's get started then. The picture is 3 times as long as it is wide.
Okay, so I'll make the width x, and then the length will be 3x. That means the area of the picture is x times 3x, or 3x squared.
Great start. I have a mat that should leave a 2-inch border around a photo that's 96 square inches. Let's see if you can figure out x now.
All right, I don't like the way he says that. I have a mat that'll leave a 2-inch border around a photo that's 96 square inches. Does he mean the photo is 96 square inches, the mat is 96 square inches, or the 2-inch border around the picture is 96 square inches? That is poorly phrased, because I wouldn't know how to set up the problem because I don't know exactly what he's talking about. Taylor's sure got her work cut out for her, though. So let's see. After this lesson, we're going to be able to answer the following questions. How can standard arithmetic operations be performed on polynomials? Adding, subtracting, multiplying. And what similarities exist between operations on polynomials and operations on functions? So let's talk about, this is some phrasing you might not have really heard us use in mathematics very much. And I'm going to do this without the lesson up because I want to talk about this. In math, we have something we call a closed system. So if we talk about integers are, whole numbers that do not have decimals. It could be negative numbers or 0 or positive or just integers. -5, 2, 7, 183. Those are all integers. And if we look at integers being added or subtracted, right? Let's say that we have all of the integers exist in this big bucket, right? In this big bucket, all the integers exist. It's an infinite sized bucket. If we pull 2 integers out there and add them, the answer is going to be another integer that's in the bucket, right? We don't have to go to another bucket. Over here is a bucket of all the irrational numbers. Over here is a bucket of all the fractions and the stuff, all of these, we got these different numbers. But the integers, if we add 2 of them, the answer is always going to be in the integers also. If we pull out 2 and subtract them, the answer is always going to be in the integers, right? That's a closed system for addition and subtraction. There's no way that you will not need to get an integer out of the bucket, right? So if we have an integer and an integer, the answer is always going to be an integer if we add them or subtract them. That's called a closed system. We don't have to go outside of the integers to get the answer. It's also true for multiplication. If I take two integers and multiply them, the answer is always going to be an integer. 2 times 4, that's 8. I'm going to pull the 8 out. That's always the same. Now, there's one case where it's not a closed system. If we divide, if I pull out two integers and divide this one into this one, that might not be an integer. If this is a 3 and this is a 7, 3 divided into 7 is 2 point something. That's not an integer, right? I'm dividing the 3 into a 7. So the division is not a closed system with integers. Makes sense. We're not going to divide polynomials in this lesson. No, we're going to add, we're going to subtract, we're going to multiply. So with polynomials, a polynomial means it has terms like 1, 2, 3, 4, 5 terms. It could be 4x squared plus 2x plus 3. That's a polynomial. It has 3 terms. It's a polynomial. With polynomials, if we add polynomials or we subtract polynomials or we multiply polynomials, the answer is always going to be a polynomial unless it's 0, right? It could be 0, which is not really a polynomial. But otherwise, it's always a polynomial. So it's really a closed system when we add polynomials together or subtract or multiply. So that's what we're going to be doing today, is looking at polynomials and just doing those basic things, adding them together, subtracting them from each other, and multiplying them. Not that complicated. So there's no way to get a fraction or decimal when you're performing integer operations. There's no way to get anything other than a polynomial when we're adding and subtracting polynomial operations. So, all right, let's go to our next page here. So the most important part of adding or subtracting polynomials is identifying like terms, right? Because we can only combine things that have the exact same variable part. Because we're going to have a lot of like terms with polynomial addition, subtraction, multiplication. So we need to make sure we know what like terms are. So if we have one of these expressions, we want to choose the like term. Like, which ones can we combine? Like if we have 2x plus 3y, we can't put those together because this one's an x and this one's a y. We can't say that's 5xy. You cannot do that when you add them. You can only add. If we have 2x plus 3x, we can add those together. Those are both x terms. That's 5x. But if we have 2x squared plus 3x, not like terms. So if we look at this, the first one they have is a 3x squared y, right? So if I click on that, I can only combine it with a like term. Well, here's a 12xy, but xy is not the same as x squared y. So those are not like terms. The only like term for this 3x squared y would be the 9x squared y. So if I add those together, I'll have 12x squared y. So I click on this and they'll disappear because those are like terms. If I do this 4f, see there's a 4f squared, but that's not the same thing. The only thing that can combine with 4f is 7f because they're both f expressions. 6xy. Here's what combines with the 12xy. Same variables, exact same variables. We can combine those. We've got 8b to the third c squared. Okay, this is a 5b to the third c squared. Then you've got, here's the f squared term, and here's the f squared term, which leaves this gh to the fourth as the other one. So that's how we look at like terms. All right, so I'm going to show this video, and then we're going to do a practice problem on paper after we do this. So this is adding two polynomials. These are both have 3 terms in the polynomial. So let's watch this on how to add those together. And really, it is, don't make it complicated because this is just adding. It's just like terms is the only tricky part.
Start by distributing any coefficients to eliminate the parentheses. There is no integer or variable before either set of parentheses. Consequently, an understood 1 is put in its place.
So there's really nothing to distribute, so they're just getting rid of the parentheses. It's just an assumed 1 out there, and 1 times that polynomial is just that polynomial.
This leaves you with 7x squared plus 3x minus 5 plus 2x squared minus 4x plus 9. The next step is to identify the like terms in the expression, because those are the ones that can be combined. 7x squared and positive 2x squared are like terms. Positive 3x and negative 4x are also like terms. And the constants negative 5 and positive 9 are like terms. Combine those terms by combining their coefficients. Remember, the variable part stays the same. While it's perfectly acceptable to show the 1 in front of the x, it's not necessary since the 1 is understood. Just be sure to leave in the subtraction sign. The sum of the two given polynomials is 9x squared minus x plus 4.
That is how we add polynomials. It's just combining the like terms. So we have another one down here. I'm going to do this one on paper so we can get some notes started on this to make sure we know what we're doing with all this. Okay, so if we have 2x to the third plus 4x squared, that's 2, minus x plus 7, plus 3x squared plus 6x plus 10, they have parentheses around, and that's just to show you that this is a polynomial added to this polynomial. But since there's not a number out here, if there was a 3 out here in front, we would have to take 3 times each term. But there's nothing out there, so we can just get rid of the parentheses. Don't even need them. Here, I'm just going to erase them. Just say we're just erasing the parentheses. Or we could write it again without the parentheses. It doesn't really matter. The parentheses are just showing you where the two polynomials are. Now, the important thing, as we said, was to make sure we combined like terms. So out here in front, we've got an x to the third power. If I look down the rest of the terms, there's not another x to the third power, so that one is just going to come down as part of our next step. That's added to nothing, so that is by itself. Then we look for the squared term. This is squared, and this one's squared. So we can combine these two terms. We've got a positive 4x, and we're adding 3x squared. 4x squared, 3x squared. So that means we have 7x squareds. 7x squareds. And I'll go ahead and put the little 2 here just to keep the color theme going. All right, what's next? Well, we have an x term right here. This is an x term, just an x, right? So we have a negative x, and we're adding 6x, positive. Negative x, positive 6x. So that gives us 5x. Right, and then what's left is we have just a number, just a constant, 7 and a 10. 7 plus 10. So this is the answer when we add those two terms together. We just have to combine the like terms. Right? This one doesn't have a like term, so it adds nothing to it. That's how we add polynomials. It is that simple. If it has a like term, combine it. If it doesn't, it just comes down to the next line. So here's the same problem right here. And they distribute the coefficients, which just meant they got rid of the parentheses because there's nothing to distribute. And then they combined all the like terms and got the same thing. 2x to the third plus 7x squared plus 5x plus 17. All right, let's look at page 3. Adding, very simple. Now let's look at subtracting. Let's see, did I do this one on paper? We're going to watch this. We have another one down here I'll do on paper. This one will do. So let's watch this first.
The first step of subtracting polynomials is to distribute any coefficients in front of the parentheses. There are no integers or variables before either set of parentheses. Consequently, an understood 1 is put in its place. When 1 is distributed to each term within the first set of parentheses, the trinomial within remains unchanged. However, a negative 1, instead of positive, is being distributed to each term within the second set of parentheses. This will change the second trinomial.
It is important to distribute a negative 1 because it changes the signs.
Now that you've gotten rid of the parentheses, identify the like terms in the expression. 9x squared and negative 7x squared are like terms. Positive x and negative 3x are also like terms. And the constants, positive 2 and positive 4, are like terms. Combine these like terms by adding or subtracting coefficients and keeping the variable part the same. 9x squared minus 7x squared is 2x squared. 1x minus 3x is negative 2x. And 2 plus 4 is positive 6. And that's it. The difference of the two given polynomials is 2x squared minus 2x plus 6.
All right, it is simple subtraction. As long as you can identify like terms, this is nothing that's difficult. You're just subtracting 9 minus 7. It's having 2x squareds. So this is not bad. It's just using polynomials instead of just regular little numbers. All right, we're going to do this next one on paper. So let me write this down and then we'll switch over here. All right, this works much like the addition. We do have something to distribute here. We have a negative. We have a negative 1. We're subtracting. Just to help us remember that we're subtracting this, we can just distribute this. So let's distribute here is just getting rid of the parentheses because it's just a positive 1. It does not change anything. But subtracting, we need to change all the signs of this. So it'd be a negative x third. It'd be a negative 2x squared. And it'd be negative 7. Right? We're subtracting 7. If we don't distribute this and we just got rid of the parentheses, we would just subtract the x third, and these would still be a positive if we didn't distribute that negative 1, and we'd get the wrong answer because we'd be adding these together. We've got to make sure we remember we're subtracting everything that's in the parentheses. So if we distribute that negative 1, that helps us remember to subtract. All right, so let's look and see what's our largest term. We have x squared, we have a 5x to the third, x squared. Okay, so we have a x to the third term. So we generally write polynomials from largest exponent down. So negative x third is our first term, right? So we got this 3. Now, what do we have for x squared? We have 4x squared right here, and we have a negative 2x squared. So 4 minus 2. Hey, we've been doing that since first grade. So that is 2x squared. So 4 minus 2. Okay, now we need the x term. There are no x terms. So we can go straight to just the plain old numbers. Negative 5 minus 7. Negative 5 minus 7, negative 12. And there's our answer. When you subtract this from this, you'll get negative x third plus 2x squared minus 12. As long as you keep track of like terms, this is real easy stuff. Just adding and subtracting. Distribute any coefficients, it just distributes that negative 1 to make sure we remember we're subtracting all of this, and then we just combine the like terms. Negative x third plus 2x squared minus 12, which is exactly what we had in our notes there. It says, what if you didn't distribute the negative? Right, then if you end up just getting rid of the parentheses, you'd have the negative x to the third, but see, these, you didn't change the sign, like I was saying, and you'll end up with an entirely different answer, negative x third plus 6x squared plus 2. So, got to make sure you're subtracting every term. Using the distributive property. So this is going to go through distributing, and I'm just going to do this on paper because you guys have been doing this for a while. You know how to distribute for the last few years. When you distribute something, um, if we're multiplying together, let's just do like if we have 3x and we're distributing that times 2x minus 1. So if we're multiplying, this is a monomial. Mono means one. There's only one term. This is a binomial, two terms. When we distribute, we just multiply this times each term, right? That's not hard. 3x times 2x. 3 times 2 is 6. X times x is x squared. Then 3x times negative 1 is just negative 3x, right? Distributing. If we have multiple terms, say we have 3x squared plus x minus 4, and we're multiplying that times x squared plus 3x. I'll multiply a trinomial times a binomial. So these two polynomials. When I do that, I have to first take this term and multiply it times both of those. The 3x squared times x squared. Well, 3 times 1 is just 3. X squared times x squared, x to the fourth. Now I need to multiply it by the second term. 3x squared times 3x. 3 times 3, x squared times x is now x to the third because we've added an x. Now I'm done with this term. Now I got to distribute this one to both. X times x squared. That's x to the third. X times 3x. That's 3x squared. Now I'm done with that. I need to distribute the negative 4. Negative 4 times x squared. Negative 4x squared. Negative 4 times 3x. Negative 4 times 3 is negative 12. And we have an x. And that's it. We've distributed all three terms to all of the terms in the second polynomial. Now it's just a matter of like terms. These are like terms. These are like terms. So we just have to simplify this. There's only one x to the fourth. We have a 9x to the third plus another x to the third. So we have 10 x to the thirds. We have a 3x squared and a negative 4x squared. So we just have a negative x squared, and we have negative 12x because there's no other x terms. So this is the answer when we multiply these two polynomials. Just distributing. Every term out here has to be multiplied by every term in here. So we just do them one by one and then simplify. So don't let that mess you up just because we're doing polynomials. You're used to distributing. When you have like a number 2 out here, you know to multiply 2 times everything. It doesn't change if we have polynomials. You're still just multiplying by everything on the right, by everything on the left. So it's not any more difficult. It's just more to pay attention to. More, and they go through examples, multiplying just a monomial, like multiplying 3x squared times that. They go through another example with you have x plus 6 times x plus 5. You do FOIL, first, outside, inside, last. And then multiplying by any polynomial. Here it takes a, just like I did, a trinomial times a binomial. And it'll walk you through the steps of doing that right there. So if you want another example to put in your notes, they have 3 examples right here. All right, now we have all the tools to help Taylor, from our introduction, find the dimensions of the picture. So we're going to watch this little goofy video again, and I apologize, the video starts over. So what they did last time is they cut it off right at the cliffhanger. Okay, that really wasn't cliffhanger. They cut it off. Now they're going to start back at the beginning and play the whole video for us. So let's check this out and see how she frames her solution, and we can figure out if that 96 square inches was the picture or the frame or the border, whatever it was here.
Is everything okay in there?
I'm fine, Dad, but the picture I took during our Grand Canyon trip fell and the frame broke. The picture looks fine, but the frame is trashed.
That's all right, it can be replaced.
Okay, I'll go get a measuring tape.
I've got a better idea. Let's use your algebra skills to find the measurements. If you get the answer right, I'll buy you a new frame.
All right, I'll give it a shot.
Let's get started then. The picture is 3 times as long as it is wide.
Okay, so I'll make the width x, and then the length will be 3x. That means the area of the picture is x times 3x, or 3x squared.
Great start! I have a mat that should leave a 2-inch border around the photo that's 96 square inches. Let's see if you can figure out x now.
Well, the total area of the mat around the photo is 96 square inches. Now, if the mat has a 2-inch border, then the length of the mat is 4 inches more than the length of the photo. Also, the width is 4 inches longer than the width of the photo. Because area is length times width, the area of the mat is 3x plus 4 times x plus 4.
You're doing great so far. Keep it going.
Now, I'll use FOIL to multiply the binomials. So the total area of the picture and mat is 3x squared plus 16x plus 16. This is also equal to the area of the mat plus the area of the picture, or 96 plus 3x squared. Now I just simplify. I got it! X is 5. The width of the picture is 5 inches. The length is 15 inches.
Awesome work! You earned your frame.
Okay, so she came up with her answer. And if x equals 5 and that picture is 5 inches tall, this girl must be 2 feet tall. Because that picture looks huge. It doesn't look like 5 inches by 15 inches. So she must be like a 2 foot tall teenager or something. It's just kind of it. So apparently the 96 inches was referring to just that 2-inch border around there. That's 96 square inches. Couldn't figure that out until she worked the problem because they didn't say that well. But yes, you're just multiplying to find the area of all this. You're just multiplying the binomials. Multiplying binomials, which is what we're going to be doing in this next page here. Multiplying binomials. Oh, we do need to talk about one thing first. Equations versus functions. Functions. So I'll stop this again because this is a term that we hammered a lot in Algebra 1 back when you had that. Equations we understand. There's lots of different equations. There's linear equations, quadratic equations, there's circle equations, there's all kinds of equations. But not all of them are functions. Remember, for an equation to actually be a function, there has to be only one y for each x, right? So like with a parabola, a normal parabola that goes up or down, we can choose an x, say x equals 2, and maybe the y is at 9, right? So, or 4, or some number, right? And that's fine. There's only one y that matches up to the x. We don't see more than one y. If we choose 0, maybe it's 0 is the y, but there's not two numbers for that. So that's a function. A general parabola, quadratic that's up or down, is a function. A linear equation. Almost every linear equation, I say almost, is a function because there's only one x and one y every point. The only exception is if you have a straight up and down linear function. Straight up and down, you have one x, but every y is the exact same x. So if x equals 2, you've got an infinite number of y's for that same x. So that is not a function. A circle is not a function. A circle is never a function, right? Because if you choose an x, there's going to be 2 y's on the circle, 2 y's on that. And so that's what this part is looking at, reminding us that all equations are not functions. But let's take a look at what they're showing as the examples. They have 4 different equations that we're looking at right here. We have x squared plus y squared equals 1. That is a circle. Go ahead and pull up Desmos here real quick. And if we put that on there, x squared plus y squared equals 1. See, that's a circle equation. That is not a function because for all of these x's inside the circle, there's 2 y's. There's a y up here and there's a y down here, right? When x is 0, there's 1 and -1. There's 2 different y's. Not a function. This one is x plus 7 equals 10. And you might think, oh, that's just a linear equation. Well, it is. X plus 7 equals 10, but it's one of those up and down ones. This is not a function because for x equals 3, y equals all of these infinite numbers, positive and negative. So there's a whole bunch of y's for that x. So that is also not a function. Y equals 2x plus 3. Well, that's a linear equation with a slope of 2 and a y-intercept of 3. So y equals 2x plus 3. That is a function. But there's only one y for every x. There's no place anywhere that there's going to be a second y. That's an easy one. And then, oh, here's a quadratic equation. Y equals, let's put that over here. Y equals x squared minus 7x plus 6. See, that is undoubtedly a function. And we can check that if we say x equals 3 and we say, let me test that from -10 to 10. I can move this line up and down and we can check any one of those. But turn on that. If I just look at the circle, see there's 2 places that vertical line touches that circle. I can zoom in there even so. When you can draw a straight up and down line and it touches your graph in 2 different places, see, that is not a function. Let's turn that off and go to this one. This one was way over here. You know, at that point right there, every y is part of that same x, not a function. This one, it is a function because the line only touches it once. So that vertical line test, it's a great way to check a graph. And this one, it only touches it once, no matter where it's at. So remember, the vertical line test can help you figure out if it's a function. If we had a sideways parabola, let's do x equals y squared minus 7y plus 6. Oh, equals. There we go. So that's a sideways parabola. A sideways parabola is not a function. See, because we got 2 y's for this x right here has 2 y's and a lot of x's. A lot of x's. Now there's x way down here that only has 1 y. This point right here, -6.25, there's only 1 y. But that doesn't matter. I only have to find one example where there's multiple y's. See, at 0, there's 2 different y's. Y equals 1 and y equals 6 when x is 0. So a sideways parabola is not a function. And this just goes through those examples well and talks about how they are more than 1 y on some of these, like the circle, 1 and -1, square root of 3 over 2 and negative square root of 3 over 2. Those are not functions in R. So this goes through those same 4, talks about how they're functions. And this talks about the vertical line test that I just talked about. So if you have this linear function right here, you can take a vertical line and as you move it from left to right, it'll only touch the line once. So it is a function. All right, let's talk about function notation just a little bit. And we'll go to our notes for that. So with function notation, if we have, all right, function notation. And this is not really new also. This is a review for you. You've used function notation. If we have y equals 2x plus 3, right? This is written in our just standard linear form, y equals 2x plus 3. We can write the same equation in function notation by changing the y to an fx. F of x equals 2x plus 3. These are the same equation. These are identical to one another. It's just this is written in function notation, and this one's not. And the reason that we like to write in function notations, it gives us the ability to set up problems a lot easier. If I say I want to know what y equals 2x plus 3 when x equals 5. So I got to write that. When x equals 5, what's this equal to? For this, I just say, hey, when x is 5, what is the value of this equation? With function notation, we just put the 5 in there. And that tells us, oh, so f of 5 means that we replaced the x with a 5, so we need to replace the x with a 5. See, since we replaced the x with a 5, we need to replace the x with a 5 and solve. So 2 times 5 plus 3 is 13. So f of 5 equals 13. We write that in function notation, which means this is the point on the line. When x is 5, y is 13. So if we graph this, the point 513 will be on the graph because we algebraically figured out what is the y when the x is 5. So we use function notation for problems like this. The other thing we use function notation for is to find the inverse. Because this lesson is going to talk about finding the inverse. And there's 4 steps to find the inverse. So let's take the same equation and find the inverse. So if we have y equals 2x plus 3. Oh, wait. If we have, they'll probably give it to us in function notation. If we have f of x, equals 2x plus 3. Let's go through these steps to find the inverse. Inverse, 4 steps. Step 1, change to a y equals. So instead of this, we change it to y equals 2x plus 3. That's step 1. Step 2, swap x and y. So the y's over here, the x is over there. I'm going to put the x over here and the y on the right side. They swap places. Step 3, solve for y equals. I want to get back to y equals. So I need to subtract 3 from both sides. So this is x minus 3 equals 2y. I've got to divide by 2. So I have x minus 3 divided by 2 equals y. Step 4, write in function notation. Since this is an inverse, we're going to write f negative 1x. This means inverse function. This means the function, this means the inverse function equals x minus 3 over 2. These are the 4 steps. Be great to have in your notes. Step 1, change to y. Step 2, swap the x and y. Solve for y, write back in function notation. 1, 2, 3, 4 steps. 4 steps. So when you're told to find the inverse of something, you need to go through these 4 steps. Write it. It may already be in y equals. If so, that your first step's gone. It's done already. But if it's in function notation, you need to change it to a y equals so you can swap the x and y in step 2. And then just solving for y, that's a simple thing, hopefully. Maybe a little more complicated on some equations, but for the most part, that's not too bad. So, all right. That's function notation, talking about using f of x so that you can say f of -6. So you can read through that if you need to. This shows more on function notation and domain and range. So function notation here, it's just using if f of x equals x squared minus 8x plus 10, find f of 4. So it's just substituting a 4 in everywhere there's an x and then solving it. So that's just an example on that. Domain and range. Oh, let's talk about domain and range just a second. So let's say, look at all the little 3's and 2's I got on the line. Okay. Let's say that I have, and yeah, I'm going to start down here so those little 3's and 2's don't mess us up. So let's say I have this equation, and it is x minus 5 divided by 2. And I say, well, if we look at that, the domain of that, what's the possible x's? X could be anything. That's infinity on both directions, right? But I'm going to say I'm going to limit the domain. So the domain is just going to be -1, 3, and 9. So I am limiting the domain by stating this right here. So if I say, what is the range of this equation when this is the domain, the range is limited as well, because I'm only talking about these 3 points, these 3 x's. So to find the range, we just have to substitute these in. We have to take f of -1. So that'd be -1 minus 5 over 2. See, I just take out the x's and put -1s where the x's used to be. -1 minus 5 over 2, that's -6 over 2, which is -3. So that's the first number in my range, because that's what this function equals when x is -1. It equals -3. If I want to find 3, I just substitute 3 in. 3 minus 5 over 2. 3 minus 5 is -2 over 2. So that's -1. When x is 3, y is -1. And then the last one, f of 9. 9 minus 5 over 2. 9 minus 5 is 4. So if I ask you for this function with this domain, what is the range? This is the range. That's the answer. And we found that just by substituting each number from the domain into the equation and then just solving. So don't let that confuse you. If it's asking about something about the domain, that means that's the only x's we're using, -1, 3, and 9. So you just figure out for each of those 3, what does the y equal? And that gives us our range of -3, -1, and 2. So it goes through that example as well. Let's look at page 6 here. Inverses. We've already went through inverse, but this talks about in general, like if you have an inverted roller coaster, that's one where the cars are underneath the track instead of on top of the track. It's kind of cool. You're hanging underneath on the whole ride. I've ridden in an inverted roller coaster. It's a lot of fun. An inverted airplane is one that's flying upside down. Not all airplanes can do that, but there are many. Inverting the colors on a photograph will turn black colors white and white colors black. So it looks really weird when you look at it with all the colors and grays that are different. So inversion is the process of reversing the order or the position of something. If we found the inverse of an integer like 7, if we're talking about addition, we could add the negative of the same number, 7 plus a -7, and it would zero it out. If we're talking about multiplying, we could multiply it by its reciprocal to cancel it. 7 times 1 over 7 would just be a 1. So the inverse could be different things depending on what functions we're using, what kind of operation that we're using to do that. So with equations and functions, finding the inverse means reversing the variables to solve for y. So we go through the steps. I'll let them go through this one as a video. 3x minus 5, that's a different one than the one we did. So we'll go ahead and watch their little video for that. And remember, you always have this one in the lesson. You can come back and look if you need to review.
First, replace the function notation f of x with y.
Step 1.
Now, switch the x and y variables.
That's step 2. Step 3 is solve for y.
Now, solve for y by isolating it on one side of the equal sign.
The last step will be to write it in function notation.
Finally, replace y with the inverse function notation. X plus 5 over 3 is the inverse of f of x.
There it is, the little -1, f of -1. X means the inverse function. So the inverse function of 3x minus 5 is x plus 5 divided by 3. And let's talk about the graph of these functions. So the function that we found on paper was, let's see, we had the original equation of y equals 2x plus 3. And the inverse of that was, let's see, what did we decide it was? X minus 3 over 2. So I got to put x minus 3 in parentheses, so the whole thing will be in the numerator, over 2. And if we look at the graph of this, it's kind of interesting. The graph of an inverse and its function that it's originally will reflect over the line y equals x. See that blue line, that dark blue line is the line y equals x. Here is the original function that goes up in the light blue, and its inverse. So if we note here that this has the point 0.03, this function over here will have the point 0.30. And that'll be true for all of the xy points. This one, it's negative 1.50. This will be 0, negative 1.5. And that makes a lot of sense because when we found the inverse, we took the x and y's and we swapped them. We traded places. And so when we end up graphing this, the x and the y's trade places. 0.3 becomes 3.0. Negative 1.50 becomes 0, negative 1.5. So any point we find on one, let's see, like 1.56, means over here we can find 6, 1.5. Well, if I get in the right place, there it is, 6, 1.5. They trade places. So it'll always be a reflection of the line y equals x because of the way that we took the x and y and replaced them. And the coordinates swap, just like we were showing. Let's see. This is a little trickier. Let's do this on paper, just have this example. So we want to find the inverse function. So it says if our function is x squared, it said find f inverse. So let's just say and find the inverse when it says this, find f of -1 squared. So our 4 steps. First, replace this as a y. That's step 1. Step 2 was to trade places. So it becomes x equals y squared instead. Step 3 was to solve for y. Well, to solve this for y, we just take the square root of both sides because the square root of y squared is just y. The square root of x is plus and minus the square root of x, whatever number x is. But remember, take the square root, there's a positive and there's a negative answer. And so then we write it in function notation, plus or minus the square root of x. Plus or minus square root of x. Now, it's interesting to note that while this is a function, this is not a function. Like, what do you mean? We wrote it in function notation, but it's not a function because if we go here and graph those, y equals x squared, there's y equals x squared, but the y equals the positive square root of x and y equals the negative, equals negative square root x. So there's the positive and negative square root of x. This is not a function. It fails the vertical line test. Now, if we limit the domain and say we only want to talk about when x is greater than or equal to 0, if we limit the domain, then we can limit the domain here, and that is a function. And it does reflect over y equals x, just like all the other inverses. But we have to limit the domain to just be the positive x's because this makes it where it's not a function anymore. It is the inverse, plus n minus the square root of x, but the inverse is not a function in this case. So there's another example on finding the inverse. You would need to go through that and put that in your notes, but it goes through the 4 steps, but we won't do that one there. And this talks about how that's not a function. Plus or minus the square root of x is both of that. We'd have to restrict the domain to just the positive values. So, all right, one more page, and then it'll give us some practice problems. Equations versus functions. So we've talked about that not every equation is a function. Okay, like every plant is not a rose bush, right? So let's see, at this point, you learn what it takes to make an equation a function. So remember, each x value, the domain, corresponds to only one y value, the range. So the graph passes the vertical line test. So you're used to writing functions using y, but functions can also be written using f of x. So consider the polynomial function y equals x squared minus 5x plus 6. To write it in function notation, you just replace it to f of x equals instead. So let's talk about adding, subtracting, and multiplying functions. So we've already looked at adding, subtracting, and talked about multiplying polynomials, but let me get another sheet of paper. Let's talk about how you would actually see this on a problem. I'm going to kind of summarize all this page with, all right. Yep, I see what it's talking about. Okay. So we're going to go through and do this whole page on notes here because you've got it in the lesson if you want to review it there. So if we have f of x equals 4x minus 7 and g of x is 10x minus 3, there's a lot we can do that. We can add the functions. So you may see this. They'll say, what's f of x plus g of x? Or they may write that as f plus g of x, just to be lazy. But you'll see it either way. And what does that mean? That means take 4x minus 7 and add it to 10x minus 3, just like we were doing before. It just means add those together. But instead of giving you the problem like this, it'll give you the problem like this. It'll say, here's f of x, here's g of x. What is it when you add them together? Well, we can get rid of the parentheses because it's just adding. So 10x and 4x added together is 14x. Negative 7 and negative 3 is minus 10. That's your answer when you add f of x plus g of x. What else can we do? F of x minus g of x. And that just means take this equation and subtract this equation. So let's distribute to make sure we don't mess this up. Negative 10x, negative negative 3. That means we're adding the 3. Almost made it a 4 for some reason. Negative negative 3. So we've got to pay attention when we've got a negative. So 10x minus 4x minus 10x is negative 6x. Negative 7 plus 3. So there it is when we subtract those two functions. We could do f of x times g of x. And a lot of times you will see that f times g of x. I'll just put a little dot there. F times g of x. That's the same thing as multiplying them together, which is the same thing as 4x minus 7 times 10x minus 3, which means FOIL. The first ones, the outside ones, or inside ones, outside ones. Yeah, FOIL. 4 times 10x, 40x squared. 4x times negative 3, negative 12x. The inside one's negative 7 times 10x is negative 70x. And then the last negative times a negative is a positive. Then we just combine like terms. So we've got 40x squared out front. Negative 12 minus 70 is negative 82. And a plus 21. So this is how you'll see that a lot of times. They will give you an f of x and a g of x and then ask you to do these things. All right, let's get to the one that may be the least familiar, because the other thing they will say is find f of g of x. Like, what? You should have seen this before, but we don't go over it very often. Well, we already said that if we said f of 4, that means instead of x, put a 4 in there. 4 times 4 minus 7, right? Solve that, because we took the x and we substituted a 4 in. So we took the x and we substituted a 4 in. Well, this works the same way, but instead of a 4, I'm substituting g of x in. So it's still 4 times, but instead of x, I'm going to put g of x there, 10x minus 3 minus 7. See, this is 4x minus 7, but instead of x, I substitute g of x in. So don't let that confuse you. That's all it means, is just take that and put it in there. Then we just simplify it. So we've got to distribute the 4. So 4 times 10x is 40x. 4 times negative 3 is negative 12. And then we still have a negative 7 at the end. So it's a 40x minus 19. That's what f of g of x is. And this is f of g of x. The other way you may see this written is they may do f, and then they do this circle. That's the same thing, f of g. F of g, that little o, the little circle's like an o, f of g. Same thing as means substitute g into the f. Now, is it the same thing if we do g of f of x? So what's going on here? I'm doing just the opposite. I'm taking g of x and I'm substituting f into that one. I'm going the other direction. So that is 10 times x, but x is going to be 4x minus 7 minus 3. So I just substitute the other direction. 10 times 4 is 40x. All right, 10 times 4x. 10 times negative 7 is negative 70. And then you got the minus 3. So this equals 40x minus 73. It is not the same thing. Not the same thing. It can be, but with these two equations, it's not. All right, I'm going to show you how to do this one problem. And this is the one that more students, here, let me emphasize this. This is the one that more students miss on the tests and on the assignments than all the other problems with these polynomial functions. This is the one. So you'll want notes on how to do this, because what you will have, let me show you, I'll show you the problem and we'll talk about this, but I want to go through it carefully so you understand. What you will have is you'll have a function and its inverse. And it'll say, prove that these two equations are inverses by doing f of g of x and g of f of x. You're like, okay, what are we talking about here, Mr. Brock? I'll show you. So let's go back to the one that we solved and found the inverse for. We found this one, right? So we had f of x equals 2x plus 3. That was our original equation. And we found the inverse. And we're just going to call the inverse g of x. But we know the inverse is x minus 3 divided by 2. So you'll have a problem that says, prove that these are inverses. Prove these are inverses. And the way you do that is you take f of g of x, and then you take g of f of x. Exactly what we were doing right here. But we use these two equations. So let's go through the first one. F of g of x. Okay, I'm going to go through this, explaining every step. So g of x instead of x, right? So instead of that, it's 2 times, but we're substituting g of x. This is g of x. X minus 3 divided by 2. And then to finish our equation, it's plus 3. Okay, so we can see what we did. We took the x's and made them g of x, which is this equation here. Now we need to simplify this. Simplify. This is just the first step, to substitute. Now we have to simplify. X minus 3 divided by 2 multiplied by 2. So wait a minute. If we have a number, and I'll just do it up here. Now let me do it in the backside. So if I have a number, let's say the number is 8, and I'm dividing it by 2, and then I'm multiplying it by 2. Well, wait a minute. 8 divided by 2, so that's the same thing as 2 times 4, and 2 times 4 is back to the 8. How did I end up with back to the 8? Well, if I multiply by 2 and divide by 2, that cancels each other out, right? If I take 8 and multiply it by 2 and divide it by 2, divide by 2, multiply by 2, I end up with just back the 8. Because this is doing the same thing in opposite. So 2 divided by 2, if I multiply by 2 and divide by 2, this is just x minus 3. Because those cancel out. And then I got a plus 3. So x minus 3 plus 3, this is just x. So when I substitute the inverse of the function into the function, it'll simplify to just be x. Well, that's good, because that proves they're inverses. That proves that this is the inverse of this. But this is also the inverse of this. If we took this one and went through the 4 steps, we'd end up with this equation. To prove this, we have to do both. We have to do both. So let's go through this, substituting f of x. So this is x minus 3, but instead of x, it's 2x plus 3 minus 3 all over 2. See, I've taken x minus 3 over 2, and I've substituted f of x. So it's 2x plus 3. So I took f of x and substituted in for the x. Now let's simplify this. Okay, there's nothing to distribute, so this is the same as just 2x plus 3 minus 3 over 2. Well, if I add 3 and subtract 3, this is just 2x divided by 2. Well, 2 divided by 2 is just 1. This just equals x. I just proved that these are inverses of each other. I proved that these are inverses by substituting both ways, simplifying, and everything canceled out to equal x. You have to show the work. You've got to substitute both ways. You got to put g of x into f of x, and you got to put f of x into g of x. And working through the simplification, it should equal just x if they're inverses. Lots of people miss this on the test, and we have the test this week. But there will be a problem just like this. Prove these are inverses by doing f of g of x and g of f of x and showing they're both equal to x. Because it should simplify to x if you do it correctly. If they're inverses, it will simplify to x. All right, let's take a look at the, we need to look at the test, but I think we're done with this lesson. Let's check it out real quick. So this was addition, subtraction, multiplication, function composition. That's what the f of g of x is. See, there's f of g of x. That's called function composition. And this does it, if you want to go through this example and look at this, this is doing it with some x squareds. So it's a little more complicated, but not really. But if it's an x squared, you just put the x squared plus 3 squared. And then substitute again for the second x. Everywhere there's an x, you're substituting. And then you just simplify it by distributing 2 times that and 4 times that and combine like terms. Distribute the 2 and the negative 4. Okay. Here's another function. 2x squared minus 5. G of x is the square root of negative 3. If you put a square root and square it, it cancels us out. So it's just 2 times x to the third power minus 5. This is a good example to check out right there. Squaring a square root cancels each other out. This is where it talks about verifying these are inverses. This is that problem that we struggle with on the test I was just talking about. You got to substitute and shows that it just equals x both ways. Let's look at the lesson summary. Adding polynomials. Subtracting polynomials. You got to distribute that negative. If you don't distribute the negative, you can have a problem there. Multiplying. If you have a monomial and a polynomial, 2 monomials and a polynomial, 2 binomials, just whatever, you just distribute. It's all distribute. Function composition, f of g of x, g of f of x, where you substitute one into another one. So it'll say you use f of x plus g of x, you'll have f of x minus g of x, multiply, or substitute one into the other. That's the operations that we looked at today. They have some practice problems. If you're not sure you got this, add these together. 8x squared plus 5x squared is 13x squared. So that could be any of those. Negative 11x plus 8x, that's a negative 11, that's a positive 8. There's only one of them that has a negative 3, so it's going to be this one, negative 3x. Excellent. So there's 4 problems there. You try 2. There's 4 problems here. This is subtraction. This is multiplying, distributing, negative 3 times everything in parentheses. There's 9 problems here. So some of them get a little more complicated, but not bad. And there's 3 problems here. It says if f of x is 3 and g of x is 6x plus 4, find, adding them together, subtracting f from g, pay attention to which one's subtracting from which, and multiplying them together. So if I have 6x plus 4, and this is 6x plus 1, I must be subtracting the f of x. This must be multiplying, and that would be adding. See, that's a great job. And there's 3 of those. Next page has a couple of practice problems. Oh, there's 6 right here on activity 1. Select the solution. If these are added, which one of these is it? Great. I'll say it's that one. Submit. Okay, it's a great job. Next, multiply. So there's 6 problems there. And here's f of x plus g of x, giving you f of x here, g of x. Check your answer. It'll walk you through it. More problems. Subtracting g of x, multiplying them, g of f of x, substituting. Then activity 2. Oh, that was activity 2. Okay. Let's look at the assignment for this lesson. Here's the assignment for this lesson. Adding polynomials, subtracting polynomials, multiplying, distribute. What represents the area of a rectangle if this is the length and the width? Well, since area is length times width, this is just multiplying. Multiply this times this. Multiplying. Now this is multiplied by itself, so it's 3x minus 5 times 3x minus 5. Multiplying. A lot of multiplying. And what should you use here to find the total revenue? Is it multiplying, adding, subtracting? So read that and figure out what you do. So this is all about adding, subtracting, and multiplying. Yes, I know I haven't done that yet. All right, we also have the test this week. So there is a practice test, and there's a video of me taking the practice test. Let's look at the practice test, see how long that is. Oh, all right. Now, why is that not showing properly? There it is. Okay. Remember back to that first lesson, simplify this. Well, that's x to the 1/6 times x to the 1/6 times x to the 1/6 times x to the 1/6, which our product property says we add those together. It's x to the 4/6. 4/6 simplifies to 2/3. Choose which one of these. Some of these are radicals, some are rational exponents. Write this in radical form. Rewrite this in exponential form. Let's see. Yep. Simplify this and write it using a radical exponent and in radical form. Divide those. Quotient property. Should have all those properties in your notes. Quotient property. This is the power property. The power property. So something like that, Multiply those. That's the product property. Simplify. If you have 49 to the negative 1/2, we want that to be a positive exponent. We put it underneath, so it goes in the denominator. Oh, find out, determine if it's an extraneous solution. What's the solution here? Oh, that's a good one. Extraneous or not extraneous? Is this extraneous or not extraneous? Find the solution here. Some say it's extraneous. Identify all the solutions. You don't have to say if it's extraneous or not extraneous. Just find the solutions. Find the non-extraneous solutions. Yeah, so that one you got to figure out which ones. You'll have 2 solutions, and which one's extraneous, which one's not. Simplify that. Remember all of our powers of I, the complex numbers. Simplify that. Simplify that by subtracting. Remember, real numbers go with real numbers. Imaginary numbers go with imaginary numbers. Simplify. Okay. And then we'll get down to f of x and g of x. Got to add them together. So that is the practice test. I'm just going to turn that in so I can go on. There is, like I said, there is a video. If you take the practice test and you bomb it like I did, I got a 42%. I may want to go back and see what did Mr. Brock do on this. So I can, there's a 45-minute video. Jump ahead, find the problem I'm looking for, and see how did Mr. Brock do it when he took the test. There's number 11. So he's working number 11. All right, let's see how many questions are on the test. We have the test this week. Part 1 has 10 questions. multiplying. Find the volume. That means you multiply this times this times this, right? Because volume is length times width times height. When you multiply those together, you'll get one of those. Simplify this. You're subtracting. You're multiplying. When you have three things to multiply, multiply two together first, and then multiply that answer times the third one. Simplify this. You got to multiply complex numbers. That's back from last week. Multiply complex numbers. Simplify. You got to change those to complex numbers. This is a negative, so there's a I comes out of that. Find all the possible values. Simplify. So we're doing a lot in this unit. We've done, let's see, I'm going to leave. Yes, I know I haven't taken that. We've done radical and rational. We've done complex numbers. We've done operations on polynomials. Part 2 is 4 questions. All right. Find f of g of x. And what does it represent? You got to substitute g into f. Multiply these two complex numbers. Solve this. What does x equal? How do you transform this to an expression that has a rational exponent? Well, you got to change it and then use the power property because you got a power to a power. Woo, man, it's a busy week. It's a good thing we got an extra weekend. We've got a short day of school, so there's no classes Thursday, no classes Friday. This is the only class we have this week. So if you have trouble, you can email me. I don't know how much email. I'll be checking emails Thursday and Friday because we're still doing school stuff. Teachers are. You're not. So I'll be checking emails Thursday and Friday. So you can still email me if you have anything. Any questions on that, but you should have enough time perhaps to do the first lesson 2.08's lesson assignment that we've done. We don't have time for the practice test or the test, but you may have time to get the assignment done for next class. So I'll give you the last, well, you only got 5 minutes, don't you? 15 minutes for class. You got 5 minutes left of class. So anyway, hope you got lots of good notes. A lot thrown at you. This class moves pretty fast sometimes. Unfortunately, it's one of those times. So let me know if you got any questions. We'll see you next time. Have a great double weekend.